next thing that we need to discuss is the attribute selection measures. And after that, we're going to discuss tree pruning method. So recall our tree termination criteria. Here, the very first one is all samples for a given node belongs to the same class. And in this example, the desirable outcome of any decision tree is to have all the leaf nodes or the terminal nodes or the leaf that without any child nodes, for those nodes to have all their observations belonging to the same class. That would be the ideal situation. So what we're saying here is we want this divide-conquer process end up with those divisions containing very pure observation. By pure observation, we're referring to the fact that all the observations in this node belonging to the same class. Therefore, we need a way to measure the pureness of a node when they're holding multiple observations. So in order to do that, the pureness measurement, or the opposite way of saying is how messy a node is can be measured using information entropy. So a set of attribute selection criteria are based on information entropy and the conditional information entropy. So therefore, we need to discuss those concepts before we move on to talk about information gain and other measures that are used to decide which attribute to use at each node. So information entropy is used widely in many disciplines, but here in machine learning and data mining, in specifically classification problems, we use information entropy to measure the uncertainty associated with a random variable, in this case, our class label. So the definition for information entropy is the follows. For a discrete random variable y, you can think of this y as our class label. It takes m distinct values, so all those m are our m class labels. Then our information entropy for this class variable going to be the negative sum for each every class, the probability for this class to happen, times base 2 log the probability for this class to happen. Okay, so pi is the probability for this y to be equal to a specific class label. So therefore, this p is the chance for this class label to happen in the dataset. So we sum over all the differences across different classes. So we have this class label variable. If we have m different classes, then we sum over this m classes. So when does information entropy take the smallest value 0? Information entropy takes the smallest value 0 when all the data set, all the observations in your data set share the same label. So in that case, you only have one label. So this is 1 to 1. The probability for that one label to happen is 100%. So here pi is 1. Therefore, information entropy is the smallest. It's 0, meaning the y, this variable, is very uniform. There's no uncertainty. All the value this y could take is that one class variable. So there's no uncertainty. Therefore, this information entropy is 0. When does information entropy take the greatest value? It takes the great value when all the classes are equally distributed. The chance for every class to happen is exactly the same, no matter which class label you're talking about. This will give you the greatest value of log base 2 m. Okay. So the interpretation of information entropy, as we have hinted already, the higher the entropy indicates the higher impurity, so high uncertainty. You have many classes with equal chance to appear, so it's harder for any random algorithms to actually label your observations properly. When you have low entropy, which means low impurity, that also means low uncertainty, means high certainty. So when you have one class dominates the distribution. Okay. So this is information entropy. Next, we're going to talk about conditional entropy.